The goal of this video is for you to be able to begin to meet the second goal for the unit on energy. Now you don't have to copy down the standard because I'm going to hand it out to you. But the goal is for you to be able to develop a model that illustrates that the release or absorption of energy from a chemical reaction system depends on changes in bond energy. The clarification statement is the emphasis is on the idea that a chemical reaction is a system that affects the energy change. Examples of models to show that you did meet the standard could include molecular level drawings and diagrams of reactions, graphs showing the relative energies of reactants and products, and representations showing that energy is conserved. So each of those is a way that you could go about meeting that goal. So we have to start then by talking about bond energy, because if your goal is to show that the energy changes are a result of changes in bond energy, you have to know what bond energy is. And it's simply the energy that's stored in chemical bonds. In order to break a chemical bond, energy is required. Because energy is required, that particular situation would be endothermic. So what you should write down from this slide is that bond energy is the energy stored in chemical bonds, and that breaking bonds requires energy so that it's and therefore is an endothermic reaction. For example, when you were little you played with Legos, you know that it requires energy to pull those Lego blocks apart. And it's the same thing in a chemical bond. It requires energy to pull the atoms apart. Now during a chemical reaction, after you break the bonds in the reactants, the products form when new bonds are formed between different combinations of atoms. Now this forming bonds process gives off energy. Since energy is given off, this process is exothermic. So endothermic means it requires energy. Exothermic means energy is given off, and therefore it would get hot, and you might see some light coming off as well. Just to summarize that, in a chemical reaction then, breaking bonds requires energy, and forming bonds in the products gives off energy. The bond breaking process is endothermic, and the bond making process is exothermic. Now during a chemical reaction, both of those things happened. Bonds break and then new bonds form. In an overall endothermic reaction, it takes more energy to break the bonds in the reactants than is given off when the bonds form in the products. Now that energy comes from the environment, so it makes the reaction feel cold because it's drawing heat away from the environment. So you'll know an endothermic reaction if the temperature goes down and it feels cold. Now in this case, the product has more energy stored in the chemical bonds than the reactants did. And we can show that by an energy diagram. You start with reactants on the left, then some amount of activation energy occurs. This would be like the spark when we did the pipette rockets. And in endothermic reactions, the products end up with more energy than the reactant started with. That change in energy is the energy that came from the environment. So the total amount of energy stays the same. The reactant started with less. We add energy from the environment, that's why it feels cold, and the products end up with more total energy. Now you should draw that picture and label it an endothermic reaction because that's one of the models that you could use to meet this particular standard that we're trying to achieve. If we wanted to show an endothermic reaction another way, we could write a general chemical equation where we start with some reactants, we add energy because that energy came from the environment. It was required for the reaction to happen. And then we end up forming the products. So if energy is a reactant, you know that that particular chemical reaction is endothermic. The energy is required for the reaction to happen. So let's do a specific chemical equation, and it happens to be the reaction for photosynthesis. In that endothermic reaction, 6 CO2s plus 6 waters plus energy. Now in the case of a photosynthesis reaction, that energy comes from the sunlight, yields sugar, which is C6H12O6, plus 6 O2s. And the amount of energy required for that photosynthesis reaction to happen is 2,802.5 kilojoules per mole. So if we were going to fill in this graph with energy quantities, the difference between here, which is the reactants, and here, which is the products, that change in energy, or delta H of the reaction, is 2,802.5 kilojoules per mole. That's the difference in energy. It came from the sun and was required for that reaction to happen. The other option for chemical reactions is that they could be exothermic reactions. And in an exothermic reaction, it takes less energy to break the bonds in the reactants than is given off when the bonds form in the products. So we don't need to add much energy to break the bonds, and we get a lot of energy given off when we form the products. That extra energy that's given off, that's no longer stored in the chemical bonds, makes the reaction feel warm. Sometimes they get actually very hot. And in this case, the products have less bond energy than the reactants. So if we were going to draw an energy diagram for this, we would start with some amount of bond energy in the reactants. Again, we have the activation energy to get the reaction started, which would be like a spark in the piezo lighter. And when we form the products, they have less bond energy. We started with roughly that much energy in the reactants, and we ended up with less energy in the products. That difference in energy gets given off as heat, so the reaction is going to feel warm. Let's do an example of an exothermic reaction. Let's say we have two reactants, which are CH4, that's methane gas, and Cl2, which is two chlorine atoms combined together so that they all have a full outer shell. In order to break one of these bonds between the carbon and the hydrogen in the CH4, it requires 105 kilojoules of energy. That's to pull off one of those hydrogen atoms from that methane molecule. We also, in order to get this reaction to happen, have to break the bond separating the two chlorine atoms, and that requires 58 kilojoules of energy. So the total amount of energy then required to break the bonds in this reaction is 163 kilojoules per mole. And I got that from adding the 105 plus the 58. That's the energy that's required to break the bonds. However, during this chemical reaction, two new bonds are going to form. A chlorine atom is going to join where the hydrogen used to be, and a hydrogen is going to join to the chlorine. So those two forming bonds give off energy. The carbon to chlorine bond gives off 85 kilojoules of energy, and the hydrogen to chlorine bond gives off 103 kilojoules of energy. So the total amount of energy given off then is 85 plus 103, which is equal to 188 kilojoules of energy altogether. The difference then between the bond making and the bond breaking is 25 kilojoules. And I got that from taking the 188 and subtracting the 163. So if we were going to write a chemical reaction for this, we would have CH4 plus Cl2 yields CH3Cl. Now I'm going to write down below just because I'm out of room, plus HCl plus this 25 kilojoules of energy extra that's given off because more energy was given off in the bond making process. If we wanted to put this on the graph then, the difference in energy between the reactants and the products, that amount of heat that got given off, would be 25 kilojoules. Now let's do a practice problem, and please write this down so you have something to go by when you guys are doing this on your own. In this particular reaction, we have two H2Os, we add 286 kilojoules per mole, and we get two H2s plus O2. The first question is the reaction endothermic, which means energy is required and it will feel cold, or is it exothermic, where energy is given off? Because the energy is written in the equation as a reactant, this reaction is going to be endothermic. And since it's endothermic and that heat is coming from the environment, that is going to feel cold. Now, if we were going to draw a graph showing the relative energies of the reactants and the products, the reactants have less bond energy. We have this activation energy, and the products are going to have more bond energy. More bond energy because that 286 kilojoules that came from the environment is now stored in the chemical bond. Therefore, the difference in heat between the reactants and the products is going to be 286 kilojoules. And that's how you draw that bond energy diagram. Let's do one more practice problem before we move on to actually doing the lab where you see some endothermic and exothermic reactions actually happening. And in the second problem, which you should also write down, we're starting with 2Na plus a Cl2, and the reaction yields 2 NaCl plus 181.42 kilojoules per mole. The significant thing here that you need to notice is that the energy is written on the product side of the equation. Since that energy is given off as a result of the reaction, this particular reaction is exothermic. Exothermic because the heat is given off. It's given off, so that reaction, if you were to touch it, would feel hot. And if we wanted to draw an energy diagram, we're going to start again with the reactants on the left. Some amount of activation energy is required to get the reaction started, so we have to draw a little hill in our graph. And the products in this case end up with less bond energy than the reactants had because that was given off as heat. The difference then, if we were going to label this bond energy, the difference between the reactants and the products is going to be 181.42 kilojoules because that's the amount of heat that was given off. The products have that much less bond energy than we started with in the reactants. Now we're done notes for this, and you're going to actually do some chemical reactions in the lab that you can use to develop models in order to meet the standard. So we'll do 4 different chemical reactions. You don't need to write these down because I'm going to hand you a lab sheet out. But just so you know what's coming up, now's the time to actually do the chemical reactions and practice making these models on your own. Good luck.